Hi, today I'm going to talk about four ways to calculate the coefficient of a multiple linear regression model. So I'm assuming that you already know the concept and the idea and the basic knowledge for the multiple linear regression. So now I'm just going to right away into the calculation for the coefficient. So first of all, let's load the data set. So here I have a data set of 263 records and then 19 columns, 19 um, uh, predictor. So it's n by m matrix. And then I also have y value, which is our dependent variables. So basically, I'm just going to calculate the coefficient and then multiply by x to predict my y value. So that's the purpose of my multiple linear regression. So when we first learn R, we know that there's a LM function, linear model function, so that we can get the coefficient right away by using this one line function here. But today I'm just going to talk about how what are the methods that is behind this to calculate the coefficient. So first of all, let's take a look at the closed form solution. So in order to get the coefficient beta for our multiple linear regression, we are going to use the residual sum of square to get the coefficient. So residual sum of square is just basically the error squares, since this is our actual y minus the y from the model, and then take the square. And then if we expand this this multiplication, and then we'll get a formula here. You are welcome to pause the video or actually derive the derivative by hands by uh, on your own, and then you can get and then you can get a better understanding for the calculation, the mathematic, and the idea behind each technique to get the coefficient of a multiple linear regression. So here I'm just going to use so here I'm just basically trying to find the minimum value of the residual sum of square, and that will give us the best line and the coefficient for our multiple linear regression. So after I expand the multiplication, I get this one here, and then by taking the derivative respect to beta, I will get this equation here. So by setting the first order derivative equal to 0, we can separate out beta here. So beta is basically x transpose x, and then take the inverse, and then multiply by x transpose multiplied by y. So here, if I run this code, you will see that my calculation by hand is actually equal to the value that I get from this LM package. So if I use this as my solution, now I can check that whether my calculation or if I derive the correct formula to calculate the coefficient. So based on this, so for in this taking the derivative and then find the coefficient that give us the minimum of residual sum of square. So you can see that we are getting the correct coefficient of the multiple linear regression. So basically, this is one of the mathematic behind the model that give us the coefficient. So the next technique I'm going to talk about is the gradient descent. So gradient descent is basically a way that you update your variable or your coefficient sequentially. So the idea is that you find the gradient of your cost function, which is in our case is still the residual sum of square, and then you find the gradient, and then you update, and then you move. So the gradient will give you the maximum decrease in that direction, and then you multiply by some learning rate, and then you keep update your coefficient, and then it will get you to the minimum of your cost function. So here again, we start with the residual sum of square, and then we expand the multiplication. So these are up to here is still the same, and then we take the derivative of the residual sum of square respect to beta. So here we have, so this is actually the gradient of the residual sum of square, and so this will give you the direction, the direction of where you will get the maximum decrease for your cost function. So that and then here I just bring the -2 and then the x transpose outside to the multiplication. So so this is my equation for the gradient, and here I'm going to use a learning rate multiplied by gradient and then updating. So my t plus 1 updates will always be the my last coefficient in the last iteration, and then minus the gradient multiplied by a learning rate. So now let's take a look. So first of all, you need to initialize a list. You need to get some random value for your coefficient. And now let's do a first update for my coefficient. And now I'm just keep updating until my there's no changes between my last two iteration. So that means my updated coefficient has converged to a stable to a minimum. So in our term, we can guarantee it's a minimum since our residual sum of square is just like a quadratic formula. So we will get a minimum, actually a global minimum. But in other, if you have a more complex cost function, then it is not the case that you can always you will always get your coefficient vector or matrix converge. So in our case, this is our very simple case. So you will get you'll get your coefficient converge. So now let's take a look what the let's take a look for based on the gradient descent method, what's our coefficient. And also let's take a look, let's if we say this is our solution. So you can see that yeah, so using the gradient descent, we also get the same value for the coefficient of this multiple linear regression. So this method is very popular for if you have a more complex cost function where there's no way you can derive this analytical solution, but you can use this gradient descent technique to update your coefficient sequentially until you can get to the point where it's very close to your minimum of your cost function. So this is a very powerful and a popular way to update or to get the coefficient. But one the drawbacks can be that you need to set up your initial values, and you also need to adjust your learning rates to get a better to update your coefficient, so that you don't if you get a very small learning rate, you will update your it might take a very long time to update, and it can be computationally expensive. And if you get a very bad starting point, you might not end up in a minimum or somewhere in the minimum, close to your minimum solution. So that's two drawbacks for this technique. And the last technique I'm going to talk about is the coordinate descent. So basically, this is something that is similar to the gradient descent, but in this technique, we are basically updating uh, one co one coefficient at a time. So we are basically, so if you have so basically this is updating your night. So for in our situation, we are updating 19 coefficient at the same within one iteration. However, this for the coordinate descent, we need to update 19 times within one iteration, since we are updating the first coefficient and then updating the second coefficient, update the third coefficient, all the way up to the 19th coefficient, one coefficient at a time within one iteration. So that's why you will see that we have a for loop embedded in a while loop. So this is another powerful technique, but as you can see that a for loop nested in a while loop will make it even more computational expensive. So it is also a powerful technique, but it will just it will require more computation for this technique. So if you can also refer to my previous video on the I think it's also called the coordinate descent and the golden ratio selection, or something like that, uh, for the coordinate descent on the two variables instead of 19 variables in this video. So and in this coordinate descent, we are also required to get a starting point, and then we also need to derive the co the partial derivative to update our coefficient. So in our case, here since we are updating one coefficient at a time, so instead of taking the derivative of residual sum of square with respect to all beta, where beta is a vector of 19 coefficient, here we are going to take the derivative of residual sum of square with respect to one coefficient. So one coefficient at a time. So here I'm not using beta, since I'm going to do the element-wise. I'm going to do the element-wise calculation instead of the matrix calculation. So here I'm just going to use W of j. So that means the jth coefficient in my W vector or in my beta vector. So that means the jth terms in of my of the jth coefficient. So again, it is still the same. So basically, it's just so here is element wise. So the residual sum of square is still the same. So we have yi minus the sum of so one coefficient multiplied by one value, and then the second coefficient multiplied by the second x, and then for each row. So I think I hope you have the basic concept for this. So I'll just go into the derivation or the calculation on how to get the partial derivative of my residual sum of square. So by taking off the d residual sum of square d the jth coefficient, so I bring the 2 to the front, and this part is still the same. And then we also need to take the derivative of using the chain rule for this. But since there's only one dj within the sum of from 1 to 19, so we only get the x for the jth coefficient instead of taking the sum. So there's no sum on the j part, since there's only one x value that is multiplying by the w of j. And then let's expand this term by bringing out wj outside to isolate the wj, since this is the variables that we need to calculate. So all the way up to this part is still the same, but notice that the summation I'm taking is not from 1 to 19, but it's only 1 to 19 except j. So it's 1 to 18 while removing the jth coefficient and the jth column in my x. And here I'm isolating the jth coefficient and the jth column of x here. So basically, it just rewrite this equation here by bringing the jth coefficient and column outside. And then I'm also going to bring out. So I'm going to use this -2 sum of I to n for xij, and use this multiply by this part, and then minus again this part multiply by this. So you have -2 sum, and then this part is the same, and then I'll use -2 sum of xij multiplied by this. So this will give me this part here. So since there's two xij here, so I'm just getting since there is also a negative sign here, so it's plus 2 times wj, and then sum from 1 to n, and then xij squared. So try to calculate it by hand on your own, and then you get a clear understanding of this partial derivative here. So, and then after this, set the derivative equal to 0, and then we will get the wj is equal to this. So try to do it. So try to derive it by hand by yourself, and then you understand. And then try to see if you can get the same result for this partial derivative. But the basic concept for the coordinate descent is that we update one coefficient at a time instead of update all 19 coefficients at a time. So here, so we started with initialize coefficient here, and then this is the function. So I create a function that I update one coefficient at a time. So now let's take a look. So this will be my first update. So my first update on the coefficient, and then I'm also going to run the. So now I'm going to run this while loop. So it might take a long time since there's a for loop nested in the while loop. So it is more computational expensive comparing to the gradient descent. So it might converge or might not. Depends on your coefficient. Well, it depends on your initial value. So, but instead of the learning rate, we for coordinate descent we don't need to specify the learning rate, since we are going to find the minimum of a coefficient, or trying to find the minimum by in one dimension, while fixing other dimension as constant. So that is the basic the concept of the coordinate descent. So again, coordinate descent is that we updating one coefficient at a time, and then that is basically finding the minimum value of one dimensional in one dimension, while fixing other dimension as constant. So similar to like a conditional probability. Basically just it just make it easier if it is easier to update one dimension at a time. So this is the difference between coordinate descent and the gradient descent. So let me stop the for loop, and now let's take a look at my coefficient here. Also, let's check if it is. So you see that even if the my matrix or actually the coefficient is not yet converged, but as you can see that my my coefficient is actually already giving me the correct or the so-called correct solution, the correct coefficient comparing to all other methods. So these are the four, or actually the three calculations to get the coefficient of a linear multiple regression model. So so uh, so here are the three techniques, and then I'm using the R package, the LM function to validate it. So again, I have this. The first one is you can just if you can just call the LM function right away to get a coefficient. But to understand what is behind this function here are the three methods that you can use to calculate the coefficient, and each of them has their own pros and cons. So you can decide to use each method based on your own needs. So um, these are all very powerful technique, especially for the last two method, for to calculate to optimize your cost function in a higher dimensional if you have a higher dimensional residual cost function. So this is how to calculate the coefficient for a multiple linear regression in R. I hope you can try to derive the gradient or the derivative by hand on your own, so that you can get a better understanding of the calculation behind by simply just using the model or the codes here. So thank you very much for watching, and let me know if you have any question.